Okay, so last section we're going to look at this week is 7.2. We're going to split this into 2 days, so we're not going to get to the next part of 7.2 for quite a while, because next week is shop, the next week is the midterm, the next week is shop, and then the next week is the next time we're going to learn something new. So I might have to remind you of a couple things, but overall the two halves of the section, they're really pretty separate, so that's a good thing. All right, so first thing we talk about in chapter 7 is a little bit more with inverse trig. From yesterday, what did we learn about inverse trig in terms of like when you use it? You use inverse trig when you're trying to figure out what? An angle. So if you're dealing with a triangle and you don't know an angle, but you know a couple sides, that's when you use it. Now, in general, any inverse function, whether it's squaring and square rooting, sine and inverse sine, any two inverse functions visually are mirror images over the line y equals x. Okay, so let me show you that with something simple, and then we'll do it with a sine function. So let's take the square root of x. And now when you take a square root, you always get what kind of answer? If you're dealing with just the principal square root. Yeah.
A whole number?
It could be irrational.
Positive.
Yeah, but it's always going to be positive. If you're dealing with a principal root, it's a positive answer. So when I graph the function and its inverse, I'm only going to compare like apples to apples. I can only get positive answers here. I'm going to make sure we only look at positive answers here. And that's why I'm typing in what I'm typing right now. If I don't do that, I'm going to be graphing more than I need. Okay, so here's the square root. And here's the square root of x. Just ignore that part. What I want you to look at is just what's in quadrant 1. I meant to put the line y equals x. What I'm trying to show you is that the graph in blue and the graph in red are going to be mirror images over the line that's going to come in black in a second. So if you took in, if this was like a piece of paper and you folded that right on that black line, the red one would land right on top of the blue one, because they're inverses. Now, that one works fine. Let's think about sine for a minute. In order for a function to have an inverse, it has to pass the horizontal line test. That's why I did this little x is greater than or equal to 0. Think of a parabola. It doesn't pass the horizontal line test. Right? A horizontal line can hit it more than once. But if you only look at half the parabola, like this, the part that was positive, the part that was greater than 0, then it does pass the horizontal line test. All right? So let's think about the sine function for a minute. Here's your sine function. Does that pass the horizontal line test? Right? No. A horizontal line hits the sine function a bunch of times. That's a problem. If a horizontal line hits it more than once, it fails the horizontal line test, which means you don't have an inverse. So actually, I already had it down here. So there's your sine function again. What we basically have to do is focus on just part of the sine function. Okay? If we want to have an inverse, we got to look at a part of this wave that you could draw a horizontal line and it would only hit it once. So let me try something like this. If I look at just that section, would a horizontal line hit that curve more than once in that window? Yeah, it still would. Right? How about if I did something, it's not perfect, but about like that? Would a horizontal line ever hit in that section more than once? No. So as long as when we talk about inverse sine, we always agree that we're going to look at that section, we can have an inverse. Right? question on that idea? So if you kind of think, well, how can you just get rid of the other stuff? The other stuff doesn't really matter. Okay? As long as you get a section that basically goes all the way from the top of the window to the bottom window, I could do it over here. We could look at that section and do inverse sine. We could, well, I'm off the screen. But anywhere that goes from the top to the bottom, as long as it doesn't do something like that, it's okay. Right? So we're going to look from there to there. So let's go like this. I'm going to put a trace around it. And let's see if we can figure out what the left and the right edge of that box in red is, okay, in degrees. These are your 4 points, or 5 points, that we would use when we graph a sine function. Okay. Look at the first cycle, right there. That red box on the right side goes part of the way through the cycle, okay? How much of the cycle is right inside the box? Okay. 1/4, a quarter of the cycle. Okay. Quarter of the cycle. In degrees, how long is that whole cycle? Hurry up. It's 360 degrees to go through the whole thing. The right edge of this box is a quarter of the way through the cycle. So where is the right edge of that box? Emily? 90. So when we talk about inverse sine, we're going to focus from positive 90 to, and this is going to be a negative, and this is also a quarter of the way through the cycle. So that's negative 90. So that's why anytime you do inverse sine on the calculator, no matter what you type in, okay, inverse sine of, let me do it in degrees. If you're dealing with radians, it'd be pi over 2 and negative pi over 2. But if you do inverse sine of 0.6, you get an answer between negative 90 and 90. If you do inverse sine of negative 0.8, you get an answer between negative 90 and 90. No matter what you type in, it's always going to be between negative 90 and 90. And this is the reason why. Because when you're dealing with an inverse, you've got to focus on a section that passes the horizontal line test. Now, you could have focused on a different section over here. That's perfectly fine. You could have. But no calculator does it that way. Every calculator focuses on that section. So that's the section we'll look at as well. All right. So the solution to our problem for not having an inverse is to take the domain of the sine function and pretend that the rest of it doesn't even exist. We're only going to focus on the section from negative 90 to 90, or as I said in radians, negative pi over 2 to pi over 2. So for a minute, I want to think about the original sine function and what we just did. So the original function, if you look at that box in red, that has a domain and it has a range. Just look at what's in the red box. Well, the domain, we just said. The domain is the left and the right edge of the box, from negative 90 to positive 90. Right? So the domain goes from negative pi over 2 to positive pi over 2, and it does include it. Right? So it does, you can put in greater than or equal to or less than or equal to. It does include it. Now, let's look at the box again, but this time I want you to look at the range. How high and low does the graph go in the box? Just in the box. That's all you want to look at. Yep.
The line itself goes from 1 to 1, but the box goes to...
Yeah, the box I drew a little bigger, yeah. But really in the box.
Are you asking for the line or the box?
The curve in the box.
1 to 1 and
It goes from -1 to +1 on the y-axis. So remember, these are going by ones. The x-axis is going by 90s, okay, if you want to think of it in degrees. So -90 to 90 in degrees on the x, +1 to -1 on the y. So that's your range. And that's from the original sine function. Now, when I graph an inverse, I said that an inverse is a mirror image over what line? It's the first thing we mentioned. Yep.
X, Y.
Can you
X
say?
equals Y.
Oh, y equals x. Yeah. Inverses are mirror images over that line. But look what that says. It says y equals x and x equals y. So what happens in an inverse is all your x's become y's, all your y's become x's. So if we know the domain and range of the original, which deal with x's and y's, we should be able to figure out the domain and range of the inverse. Just everything switches. So for the inverse sine function, your range, well, let's start with domain. Your domain is going to be -1 to 1 on the inverse. Why? Because that was the range on the original. And now for inverse sine, your range, well, I'm going to go back to the original and look at the domain. So if you know the domain and range of the original function, just switch them, and now you've got the inverse function. Just let y equal x and let x equal y. So when I graph it on the calculator, the inverse is just going to be this little section from -1 to 1 on the x and -π/2 to π/2 on the y, if I'm in radians. What's -π/2 and π/2 in degrees? Yep.
-90 degrees.
So I'd have to set my window -90 to 90 if I want to do degrees. Okay, but let's take a look at what inverse sine looks like. So I'm going to type in, I'll get rid of all this first. Let's type in inverse sine of x. And now I'm in degrees. So domain, -1 to 1, that's easy enough to set. I'm probably going to go like -2 to 2. So it's not on the edge of the screen. And now the second one is your degree, right? The y-axis here represents an angle. In the original function, the x-axis represents an angle. Now it's the y-axis. All right. So I'm in degrees. I'll go like -100 to 100. Okay, so it's not right on the edge. So -100 to 100, and hit graph. And that is what inverse sine looks like. It is a mirror image over the line y equals x of a sine curve. It's a little harder to visualize because it's all curved, but it is a mirror image. If you wanted to do the same thing in radians, you can't just press radians and hit graph. You're going to get something like that, which looks pretty awful, right? That's not what it's supposed to look like at all. So when you do it in radians, domain is okay. Just change this to -2 to 2. Because π/2 is about 1.5. So if you go -2 to 2, that should be good enough, and you should get a picture. Looks exactly like what I had before. There you go. So there's the same picture in radians. Any questions on that? And that's it. It doesn't go off the screen. It doesn't keep going up. There's a dot here and a dot here, and they're connected with that curve. That's the whole picture. All right, so let's take a look. Inverse cosine. Well, cosine, we have the same problem. It's a wave. It fails the horizontal line test. So if you graph cosine, you can see it. Let's speed it up a little bit. it fails the horizontal line test. So let's try the same thing. Let's try that negative 90 to 90 trick and see if that works for when we deal with cosine. Let's see. So negative 90 is right there. Positive 90 is right there. If I set my window to just what's in red, would that pass the horizontal line test? No. That means for inverse cosine, you can't do negative 90 to 90. But I could slide it a little bit. Right? Let's broken box. Let's slide it right there. What if I make my box a little bigger? What if I look at what's in that box? Does that section pass the horizontal line test? Yeah. So we could look at that section, and there's a ton of other sections you could look at, as long as you just get one that passes the horizontal line test. That's the one that calculators use. So that's the one we'll use. Does anyone have a guess what the left and right edge are for that box? Yep.
0 to 180.
It's 0 to 180, or in radians, 0 to pi. So that's what we're restricting the domain of the original. That's going to turn into what in the inverse? That's the domain of the original. So it'll become the range. So when we deal with inverse cosine, the range is 0 to pi. Now, how did I figure out the domain of the inverse? Well, think of the range of the original. Cosine goes up to 1 and down to negative 1. That's the range of cosine. That becomes the domain in the inverse. Okay, I'm not going to graph that one because we really don't focus on any graphing by hand with inverse trig functions. Right, and inverse tangent. Well, let me graph regular tangent, and let's see if it passes the horizontal line test. Right, so let's graph tangent. Does that graph pass the horizontal line test? What do you think, Nancy? No, because if you put a horizontal line, it's going to hit it a bunch of times. But is there a way that I could kind of block everything else on the screen and focus on something where it would pass the horizontal line test? What do you think, Gabe?
Could you go negative 90 to 90?
Yeah, you could. You could go negative 90 to 90 again. You just got to be a little bit careful the way we say it. But if you go negative 90 to positive 90, and you just focus on what's in that red box, you can do inverse tangent perfect. All right? If you didn't focus on a section that passed the horizontal line test, what that would mean is when you do inverse trig, you would get an infinite amount of answers. Right? You can't have an infinite amount. We all want to have one answer when we do inverse trig. That's why we focus on a section that passes the test. Now, what does this graph have that the other two? This graph has something special. Remember, I mean, it's not a continuous function. It's not connected. You have to pick up your pencil to draw it. So that usually means you either have a hole or something else. Yeah. You have asymptotes. So when Gabe said we can do negative 90 to 90, we can. We just can't include the negative 90 or the 90. So that's the domain of the original. What does that become in the inverse? Joe?
The range?
Yeah, it's going to become the range. So the restriction on the domain we got to put in to make everything work is negative 90 to 90. That's going to become the range. Now notice I put parentheses. That's because you can't, they're asymptotes, you can't reach them. What kind of asymptotes are these? Vertical or horizontal in the original? Oh, Justin?
Vertical?
They're vertical. So what kind of asymptotes do you think you end up with when you do the inverse? What kind of asymptotes do you end up with? Yeah? Yeah, horizontal. So all the x's become y's and the y's becomes the x's. So vertical asymptotes in the original, horizontal in the inverse. Now, domain, a little different than sine and cosine. The range of the original is negative infinity to infinity. It goes up and down forever. While in the inverse, it's not going to go up and down forever. It's going to go left and right forever. It's going to switch. So I'll graph that so you can see it. But you're going to have horizontal asymptotes exactly where you would have had vertical. They would have been at negative pi over 2 and pi over 2. They're still at negative pi over 2 and pi over 2. They're just not on vertical anymore. They're horizontal. Okay, so let me graph that so you can see what it looks like. All right, so domain, that's my x min and max. Well, it's going to go forever. So negative 10 to 10 is probably good enough. Now my range represents an angle from negative pi over 2 to pi over 2. It's like negative 1.5 to 1.5 roughly. So let's just go negative 2 to 2. And there's your graph of inverse tangent. Okay, if I zoom out more on the x-axis, you'll definitely see it's an asymptote. It really levels off. The more I zoom out, the more exaggerated and sharper I make that curve look. But that's basically what inverse tangent looks like. Right. So any questions on the domain and ranges of the inverse functions? It can be a little tricky to remember, but what I always do is I just try to remember the originals. And if I can remember that, just switch them. And now I have all the inverses. Okay. All right, so I told you that inverse sine and regular sine cancel out. Okay. If you do something like the inverse sine of the sine of 0.5, you get the same thing back you started with, 0.5. And we did this yesterday when we were solving triangles. We took the inverse sine of both sides, and I said that it would always work. And I think I gave you guys a couple examples, like 75, but you have to be in degrees. So if I do it in degrees, you get the same thing back that you started with. But you reach a point where all of a sudden you don't. If you try to take the inverse sine of the sine of, say, 95, I got 85 back. So there's a pattern to the answer you get back, but it's not the same thing if you go beyond a certain point. And the point that you can't go beyond, we already mentioned earlier. It's negative 90 to 90. So don't write this part because you need to be able to read your notes. But this and this basically cancel each other out. And the answer that you get is whatever you typed in to begin with, as long as what you typed in is between negative 90 and 90, or negative pi over 2 and pi over 2. Now, how come yesterday that wasn't a problem? Why would the number that we type in here, how come we know the answer would always be between negative 90 and 90 when you're solving for an angle in a triangle? In fact, we can even do better than negative 90 to 90. But how come it's at least between those two numbers? Yep. Bob?
Because if you're given a right triangle that already has the 90-degree angle, the other two angles have to be in between 90 so they can add up to 90.
Yeah.
And because the angles of the triangle have to add up to 180. So.
Yeah. So when you're dealing with a right triangle, you're guaranteed that x is always between, I can do better than negative 90 and 90. I can say between 0 and 90. So that's why this formula always worked yesterday. Right? So look at the restriction. The restriction is from negative pi over 2 to pi over 2. That's the same restriction that we put on the domain of that function. We said negative pi over 2 to pi over 2. All right? Let's look at this one. It's a little different. Now the inverse is on the inside, and the regular sign is on the outside. Right? There's a restriction here too. Right. Let's go back to inverse sine for a second. Just look at that table we just made. I want to see if we can notice something. So when we did the first formula, the restriction came from the domain of the inside function. The domain of the inside function was negative pi over 2 to pi over 2. Now look at the function that's on the inside this time. It's inverse sine. Let's go back and look at the domain of inverse sine. What's the domain of inverse sine? Gabe?
Negative 1 to 1.
The domain is negative 1 to 1. That's the restriction here. The restriction on these formulas always comes from the domain of the inside function, if that helps you to remember it. All right, so you could type in something like sine of inverse sine of 0.6. And when you hit enter, you're going to get 0.6. Somebody give me something I could type in here that wouldn't work. We know what it should be between. Give me something that's not between those two numbers. Robin?
A negative?
Sure, like negative what?
15.
Negative 15. So if I try to type that in, it's not that I get something different back. I don't even get anything back. Can't even do that. Okay? So if you're dealing with inverse on the inside and you're trying to cancel it out, that number's got to be between negative 1 and 1. Okay. Let's look at this one. It's not really important if you call this formula 2a and 2b. I'm just, if we need to go back to them, I'll say look at formula 2a so you have a name for it. Okay. Inverse cosine and regular cosine always cancel each other out as long as x is between. And now think of the domain for cosine. It's when I had the window on the screen and I drew the red box. What did we restrict the domain to for cosine? We couldn't use negative 90 to 90. That didn't work. What was it? 0 to 180, or in radians, 0 to pi. Yep, so there's your restriction there. And then formula 2b is the same functions, we're just switching the order. Now the inverse is on the inside. Right, so again, I look at the inside one, and I say, okay, what's the domain of inverse cosine? If you know that, that's your restriction. If you get stuck with that, and you're like, you know what, I don't remember the domain of the inverse, okay, then think of the range of the original. It's the same thing. So what's the domain of inverse cosine? Or what's the range of regular cosine? Either way. Yeah? It's negative 1 to 1. And we are a little picky here about whether it has the equal to or not. These are all equal to so far. When you get into tangent, then you got to be careful. Okay. And you could try these with examples on the calculator, but I'm not going to keep trying different numbers. So inverse tangent, regular tangent, cancels each other out. As long as x is between, what's the domain of tangent? Our restricted domain. Yep.
-pi/2
And negative pi over 2 to pi over 2, including or not including?
not including.
Not including. So negative pi over 2 to pi over 2, not including. And now, then the A version of the formula, that's pretty much the one you do when you're solving triangles. The inverse is on the outside, regular is on the inside. The B version of the formula, we're going to talk more about that in part 2 of this lesson. So the B version, tangent on the outside, inverse on the inside, cancels each other out as long as x is between. And now think of what's the domain of inverse tangent. When I drew inverse tangent, how far left and right did it go on the screen? Or think of how far up and down regular tangent goes. Either way. Okay?
Negative infinity.
Yeah, so this one always works. It's negative infinity to infinity. None of these restrictions were important yesterday with the A version of each formula, because when you're solving a right triangle, you're always going to be between negative 90 and 90. You're always going to be between 0 and 180. You're always between negative 90 and 90. That restriction didn't matter. But if you're not dealing with just triangles, then yes, it does matter. All right, so we've done this at least 6 or 7 times, all the transformations. Every letter that you see there does exactly the same thing that it does in every other function we've studied all year. Okay, so I'm not going to write everything out. I'll say it. If you need to write it, you can. But what does A do to the function? Yeah, Blake?
Moves it right or left?
Yep, it's going to move it left or right. If it's positive, it would move it which way?
Right.
Left. If it's negative, it moves it right. So A is your horizontal shift. What about B? What does B do? Yep.
Isn't that horizontal stretch?
That's your horizontal stretch. Now, if you put in a really big number for B, like 50, do big numbers cause the graph to stretch or compress? Yep. Compress. Everything inside is backwards. All the horizontal stuff is backwards. A big number for B actually makes it compress. A small number for B, like 1/10, would make it stretch. So all your horizontal stuff is inside. And we had an addition and a multiplication. Now we're going to go outside, and we have an addition and a multiplication. So the next one would be C. What kind of transformation is C? Yep. Vertical stretch. And this time, a bigger number does stretch it bigger. A smaller number would compress it smaller. Before we do D, something could happen with B and C we've talked about. What could B and C, if this happens, you'd have to make sure you remember to do this when you graph it. Yep.
If there's a negative, it's a reflection.
It's a reflection. If B is negative, that's a horizontal reflection. That means something like this. You flip left to right. If C was negative, that's a vertical reflection, which means you would flip up to down. Okay? And then D, that's your vertical shift. Positive is up, negative is down. So there's no change from everything we've done all year with that. Okay, so we'll see if I do a problem with that. But the kind of problem you'd probably see is describe the transformations in this problem. So if that were the problem, you'd say a horizontal shift left 3, and it's horizontally compressed by a factor of 2. That's what I do. Okay, but we've spent a lot of time on that. All right, so what we want to be able to figure out is when you do a transformation, what happened to the domain and what happened to the range here? Well, the 2 transformations that I did right there, did they affect the domain or the range? It was a horizontal shift and a horizontal stretch or compression, really. That affects the domain. Horizontal is left and right. Left and right is the domain. I didn't alter the range at all here. Now I did. Okay, now I shifted it up 6. So you want to be able to look at a problem like that and figure out the new domain and range. Well, to figure out the domain, what you want to do is create a compound inequality. You take the argument, you put that in the middle. And then on the left and on the right, you put the bounds of the original domain. So for, let me think for a second. For inverse sine, that's negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2. And now I would solve that and get x by itself in the middle. So in this case, minus 3, and then double everything. We're going to do an example. But so put the argument in the middle. So remember, the argument is what's in the parentheses. And then solve the inequality. Make sure you remember your rules. If you multiply by a negative, you're going to flip the sign. All that stuff still applies. And then to find the range, well, all we have to do is take into account letters C and D in that order. That's why I wrote them A, B, C, D. If your range was originally negative 1 to 1 and you tripled it, well, now it's negative 3 to 3. And then if you shifted it up 1 unit, well, if you had negative 3 to 3 and you shifted it up 1, that would be what? Negative 2 to 4. So that's pretty much how you find the range. Take into account any vertical stretching you do first. So multiply each number in the range by the stretch or the shrink. And then take into account any shift up or down. So add or subtract whatever you shifted up or down as the last step. We'll try one of those two. I think the hardest thing is just remembering all the original domains and ranges. 2 of them are negative pi over 2 to pi over 2. One with an equals, one without. And the other one is 0 to pi. Inclusive. Okay. Closed interval. All right, so again, we're not really going to do any graphing by hand. I just want you to be able to find the domain and range of that. Well, how many transformations are happening in A? Could be a lot worse, but there's only, how many? There's only one. So if there's only one transformation, then one of those domain or range is going to stay the same. Which one is going to stay the same? Robin?
Range.
The range, yeah. We're not doing anything outside the parentheses, so the range stays the same. Can someone remind me, what is the range for inverse sine? Again, if you can't remember the range of the inverse, think of the domain of the original. Yep.
Negative 1.
We're going to use that, but that's going to be for the other part. Yep.
Negative pi over 2 and pi over 2.
Negative pi over 2 to pi over 2. That's the domain of the original, which becomes the range in the inverse. Now, Robin just told us the domain, what it starts out as. You said it was what again?
Negative 1 to 1.
Negative 1 to 1. So I'm creating a compound inequality with x in the middle. The original was closed. You could include the original, so we can still put the equal to's here. It's just tangent that doesn't have the equal to's under one of them, or actually both of them. All right, and now how would we solve that for x? Yeah. Let's divide everything by 2. And that did exactly what it should have. We put a bigger number in front of x. The domain just compressed. It used to be negative 1 to 1. Now it's shortened to negative 1/2 to 1/2. That's what should have happened. Any question on finding the domain and the range stayed the same?
And we need to
All right, same setup here. We've got a number in front of x again, so we already know range is going to stay the same. So let's copy that down. Negative pi over 2 to pi over 2. Now, before I find the domain, I've got a small number in front of x. I think of numbers less than 1. Those are small. What should happen to the domain? Should it compress, or should it get bigger? It's going to stretch out. Jarek?
It will stretch.
It's going to stretch. The domain should get 3 times the size that it is now. What is the size now? We need to start with that. How about Natalie? Can you tell me what the original domain is?
It's 1, negative 1 to 1.
So it's negative 1 to 1. And we're going to put the argument in the middle. And we're going to solve that inequality to get x alone. So Justin, how do I get x by itself here?
Multiply everything by 3.
Yeah. So your new domain is going to be negative 3 is less than or equal to x less than or equal to 3. So negative 3 to 3. Okay. So there's your domain and range there. Let's find something with range. There we go. How come I said I wanted to find something with range, and that one is range. How come? Why is the range being affected this time? Yeah.
Because the +2 is in the parentheses.
Yeah, the +2 is outside. That's a vertical transformation. So your domain stays the same. Right? So we go back up. Original domain, negative 1 to 1. And now, to find the range, well, let's think of what the range was originally. Someone remind me, what's the range for inverse sine? Rob?
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. And what's the transformation we're doing here?
You're adding 2.
Which does what?
Goes up 1.
It goes up how many?
Or 2.
2. So it shifts up 2. There's not really a nice way to write this answer. It's negative pi over 2 to pi over 2. You're just shifting that one up 2 and that one up 2. If you wanted to write it as a decimal, that would be negative 1.57 plus 2. So you could do that, and then 1.57 plus 2, 3.57. So 0.57 to 3.57. But that's it. That's your range. Okay, let's try an inverse cosine, and then we'll do one inverse tangent. Okay, how about Joe? What's going to stay the same here? Domain or range?
Range?
Why?
I have no clue.
What's the 5 doing?
That's the something stretch.
That first word that we need to replace with something is the key to figuring out which one. So it's the something stretch. What kind of stretch? And this will tell us which thing is changing. Yep.
Vertical.
It's a vertical stretch. Things are changing up and down. Range goes up and down. So range is changing. So domain stays the same. We haven't done domain of inverse cosine in a while. What's the domain of inverse cosine? Yep, Kaya?
Negative 1.
Yep. It's a little tricky to remember at first, but eventually you get better at it. So we've got negative 1 to 1. And now we already said we're stretching the range by a factor of 5. Well, let's start with the original range. Someone remind me, what's the original range for inverse cosine? Yep, Kaya.
0, 9,
For 0 to pi.
0, yeah, we could go 0 to 90 if you're doing degrees, or 0 to pi, and we're going to make it 5 times as big. So now it's going to go 0 to 5 pi. Or 0 to, if you did it in degrees, 450 degrees. Okay, now we've got a number inside and outside. So does that mean both the domain and range are going to be different?
Yes.
Yes? Normally I would agree. We're going to be careful though, we have inverse tangent. So as we go through, let's see what happens. What's my original domain for inverse tangent? Think about inverse tangent and how far left and right it goes. Yeah?
Negative to infinity.
It's negative infinity to infinity, and we're going to compress that by a factor of 2. So what happens to the domain? If you compress negative infinity to infinity by a factor of 2. Okay. It stays the same. So yes, normally this would have affected the domain, but since you had an infinitely large domain, and you cut it in half, you still have an infinitely large domain. Okay, and the range? What's the range on this one? And just be careful how you say it. Because it's similar to another one, but yeah?
Negative pi over 2 to pi over 2, not including
Right. So that all that means is instead of a bracket, I'm going to use parentheses. And it's negative pi over 2 to pi over 2, but we've tripled it. So you take these two numbers and triple them. So negative 3 pi over 2 to 3 pi over 2. All right, so we've done a bunch of those, but any questions on finding the domain and range of an inverse trig function? You don't have to worry about inverse secant, inverse cosecant for this stuff. Yeah.
Can you go back up for a second to
B?
D?
D.
Thank you.
Anyone good with that? All right, so what's this? Just identifying the transformations. You don't have to tell me domain and range. So if you're going to identify the transformations there, it's not quite set up to do it yet. What do you think you should do first? And then we can identify transformations. Yep.
Distribute the 1/4.
Yeah, distribute the 1/4 so you've got this. Right. Now we can go through all the transformations. All right, let's see. It looks like we've got 4 transformations and we have to put them in the correct order. Okay, so what's the first transformation you would do? We've got them all. We've got all 4 of them. Well, we don't have any reflections, but we got everything else. Yep.
Would it be the plus 8, the x plus 8?
Well, let's pretend this is gone now because we rewrote it.
The x plus 2.
The plus 2. What's the plus 2 going to do?
It's going to move it to the left or right.
Which way? The other way. Left. There you go. How many?
2.
Shift, left, 2. Good. First thing. What's the second thing that's going to happen? Yeah?
Stretch by 4.
Right. It's really a stretch by a factor of 4. Small numbers actually stretch it bigger. So that's a stretch by a factor of 4. I mean, I guess you could say shrink by 1/4. That's kind of like saying a double negative. It's kind of weird to say it that way. It's like saying move down -2 units, when you could just say move up 2. So I think that's a simpler way to say it. The next thing, we've got the 3 on the outside. It's a vertical stretch by a factor of 3. And what about the last number? What's that going to do to my graph? Yep.
Move it down 5.
Yep, so shift down 5. So same kind of thing we've done with every function we've studied all year. Any questions on that? All right, so I think last thing is really just a calculator thing. So we're just going to practice typing in things like that on the calculator, and we kind of did that yesterday. So can someone remind me, if I want to type that in, what buttons do I have to press? Because I don't have a way to get to this button directly. So what do I have to press first? Emily?
Second sine.
Yeah, second sine, and now just type in your argument. Unless you have something else coming after it, it's not important if you really close it. I closed it. Now, when I hit enter, we know that inverse trig is always used to solve for an angle. I'm in degrees. So when I write my answer down, I need to put a degree symbol on that. If you write that, I'm going to mark it wrong. Because what you're telling me there is that's an answer of 30 radians. No, that's 30 degrees. So if I type in this, and I hit enter, what should I get back as my answer? 0.5. We're just going back and forth. It's like squaring something and then taking the square root. I took the inverse sine of something and then I took the sine of it. You just went back and forth. You didn't have to. I'm just showing you that. How about this one? Inverse sine of negative 0.7. I'm sure we know how to type it in, but is it going to work? Think of what the domain is supposed to be. What numbers are you allowed to plug into inverse sine? Between what and what? So think of the domain of inverse sine, or the range of the original. How high and low does the original sine graph go? Either way.
Isn't it 0, 90?
That's the other thing. Yep.
Negative 1 to 1.
The domain of inverse sine is negative 1 to 1. So the answer to my question is this is going to work fine. What it's going to be, I have no idea. But that's what it is. Negative 44.43. Anything else I need on that? Degrees, yes, because that's an angle. Now how about this one? Inverse sine of 1.2. What's going to happen when I type that in? It's not going to work. Okay, you can't go above 1. If you try, the calculator gets annoyed with you, and it says error domain. Okay, you can't go above 1. All right. So for this one, you'd write no solution, undefined. And you can do inverse cosine and tangent the same way. And just remember that there's also domains for those you have to pay attention to. Not so much inverse tangent. Inverse tangent, the domain is all real numbers. So. Okay, any questions on that? All right. So this is the last homework assignment for this term, or if I end up doing my grades early, I'll count this as the first homework assignment for next term. Either way, it's going to be a homework assignment. I'm just not sure which term we'll put it on. So it's page 394, 1 through 9, 13 to 20, 22 to 24, and 27 to 33. Okay, so that's due on, is it the 14th?
Yes.
So that'll be due on the 14th.